Let's talk about warnings about correlation. Statistics books talk about explanatory and response variables. What do they mean by this? Sometimes we believe that a change in one variable causes a change in another variable. For example, in general, the weight of a car affects the gas mileage. And maybe your car is heavy because it's really loaded down with stuff. I know what it's like to drive across the country, and gosh, I felt like this. Or maybe it's just a huge car, even if it's not loaded up with stuff. Whatever the case, there's a relationship between the weight of a car and the gas mileage. So again, in general, the weight of the car affects the gas mileage. In this case, the explanatory variable is the weight because it explains the other variable. In other words, the weight explains the gas mileage. And the response variable is the gas mileage because it is a response to the other variable. This is what a scatter plot would look like. Notice there really does seem to be a relationship between the weight and the gas mileage. So these are some pretty heavy cars here, and they get some pretty cruddy gas mileage. These cars are pretty light cars, and they have very good gas mileage. The explanatory variable tends to go along the x-axis. In this case, that would be weight. The response variable tends to go along the y-axis. That would be the gas mileage in this case. Sometimes we believe that there is a relationship between two variables, but we do not necessarily believe that one causes the other. In this case, either could be regarded as the explanatory variable, and the other would be the response variable. So for example, there's a correlation between monthly ice cream sales and monthly air conditioner sales. Neither causes the other. Instead, both are caused by warm temperatures. It's not as if people start buying ice cream because those air conditioners are selling, or vice versa. In this case, either could be regarded as the explanatory variable, and the other would be the response variable. By the way, when two variables are correlated, not because one causes the other, but because both are caused by a third variable, we say that their third variable is a lurking variable. Sounds ominous. For example, there is a correlation between monthly ice cream sales and monthly air conditioner sales. Both are caused by warm temperatures, which would be a lurking variable. Okay, now let's get to these warnings about correlation. These are things to bear in mind as you deal with correlation. Be careful. Correlation does not imply causation. You've already seen that. Key idea. Don't forget it. No, don't need to say any more about that. Here's another warning about correlation. Correlation and scatter plots involve quantitative variables. You can't say that there's a correlation between height and eye color, because height is quantitative, but eye color is categorical. There may be an association between the two. This is a vague term we use to describe the relationship between two variables, whether the variables are categorical or quantitative. So you can say there's an association between the two, but you can't use the term correlation. That's reserved for quantitative variables. Both have to be quantitative. Another warning, correlation is appropriate only when the relationship is linear. In other words, when the relationship follows a straight line. For example, in this case, we would not use correlation to measure the strength of the relationship between x and y, because these data do not appear to follow a straight line. Instead, they follow a different kind of curve. Another warning, correlation is not appropriate when there are outliers. Here's a good website I found that gives an example of this. For each scatter plot above, how does the outlier affect the correlation? Well, here in this first case, the outlier decreases the correlation. There is really a pretty strong correlation here, but this one outlier can really throw things off and deceive you into thinking that there isn't a strong correlation when, in general, there is. And in the same way, this can substantially increase the correlation. You know, there's a good correlation, but if once you throw that in, that substantially increases it, and it can deceive you into thinking that the relationship is stronger than it really is. So correlation is really not an appropriate measure if there are outliers. Another warning, the correlation between x and y is the same as the correlation between y and x. It's not going to matter. Another warning, correlation does not depend on units. We talked earlier about the correlation between the weight of the car and the gas mileage. The correlation would not change if we switched from pounds to tons or to ounces or really to any other measure of weight. It doesn't matter. It's still going to be the same correlation. Nor would it change if we standardize the variable. In other words, if we converted it to z-scores. That doesn't affect the correlation at all. Remember that correlation itself, correlation is a number between -1 and 1 Correlation has no units. It's just a constant between -1 and 1. By the way, Wikipedia has a list of humorous units of measurement. For example, the beard second is defined as the length an average beard grows in 1 second. Helen of Troy from the Iliad is widely known as the face that launched 1,000 ships, thus 1 millihelen is the amount of beauty needed to launch a single ship. And Andy Warhol said everybody will be world famous for 15 minutes. So Warhol represents 15 minutes of fame, so 1 kilo Warhol is 15,000 minutes, or 10.42 days of fame.